proper understanding of the first order low pass filter and subsequent the second order low pass filter, right, will take you to the easier understanding of the second order high pass filter also. So that is the reason why I deliberately did not consider the first order high pass filter as I did in the previous case, right? So now we shall directly move on to the second order high pass filter. Please have a careful observation of this diagram. You have again the two rungs here in the ladder, C1, C2 and R1, R2, but their positions are now interchanged because we will have to deal with the high pass filter, right? Accordingly, the positions of the capacitor and the resistance are changed now in comparison with the low pass filter, right? Now, you see here the explanation goes like this. Of course, the frequency response you can see here. This we have already seen in one of our earlier slides, right? At higher frequency, right, again, your XC1 and XC2 are much smaller than R1 and R2 by virtue of their positions with respect to the R1 and R2. The capacitors have now come in series, unlike they were in parallel in the low pass filter, right? So at higher frequency, their values are going to be, the XC1 and XC2 are going to be much smaller than R1 and R2. So therefore, you will not be, able to have any attenuation at the output. So your output will be simply the input with approximately gain equal to 1. Right? But at the lower frequency, right? So you have got two types of the attenuation. Provided by the two rungs of the ladder here, right? So one is due to R1 and C1, right? So due to R1 and C1, there will be an attenuation of minus 20 dB per decade, which is added by the attenuation due to the another rung, that is R2 and C2, as you can see here in this diagram. Another minus 20 dB per decade will be added, which will have a total attenuation of minus 40 dB per decade, right? So at the stop band, right, up to a frequency Fc, all the signals of the lower frequency, that is below Fc, will be attenuated, and in the pass band, which is beyond Fc, all the high frequency signals will be passed. It is just the converse of what we have seen in the case of low pass filter, right? So this is the simple explanation. Please write these explanations whenever the questions are asked on these things. Do not give the shortcut methods of, or the shortcut ways of answering the things. Please give your explanations very clearly, and accordingly in our next slide, right, we shall have the the design aspects of this second order high pass filter, right? So let us move on to the next slide now. Now, the design of this second order Butterworth high pass filter goes in the same lines of the design what we did in the case of the low pass filter. But one important thing to be noted here, again, as we have seen in the case of the low pass filter as well, the cutoff frequency occurs at XC1 is equals to root 2 R1 and XC2 is equals to R2 divided by root 2, right? So these are the the conditions or the relationships that are supposed to be held between R and C at the cutoff frequency, right? So therefore, your R2 is equals to root 2 into XC2 at cutoff frequency. Needless to mention that your R2 is 100 times IB max, referring to the diagram, right? And your R1 will be R2 by 2 now. Here, please look here, right? In order to satisfy the conditions of the relationships between R1 and C1 and R2 and C2 at the cutoff frequency, your R1 should be equal to R2 by 2, right? And accordingly, you have XC1 is equals to root 2 into R1 at cutoff frequency. Please recall, it is at 3 dB lesser gain, right? The cutoff frequency takes place at 3 dB lesser gain. You can even refer to the frequency compensation circuits which you have studied earlier, right? And finally, you have R3 is equals to R2, right? R3 is equals to R2. So these are simple the design aspects as long as the second order high pass filter is concerned, and accordingly we will look at one simple example here, right? Design a second order high pass filter to have a cutoff frequency of 12 kilohertz. Use IC715. Use IC715, which has got, IB max is equals to 1.5 microampere. So this is slightly different here compared to the conventional examples that we have been taking earlier, right? And also estimate the highest signal frequency that will be passed. So slightly different, but it is very simple. Anyway, we will look into these things. Recall the circuit diagram of the second order high pass filter. Again, by looking at the design steps, the first few steps are very simple and they are common. So you have R2 is equals to 46.6 kilo ohm because it is 100 times IB max, and your IB max is now no longer 500 nanoamperes as we have taken it for IC741. It is for IC715. So it is specified as 1.5 microampere. So you get R2 equal to 46.6 kilo ohm, and again the R1 and R3 values can also be easily evaluated with the relationship of them with respect to R2. R1 is equals to 23.3 kilo ohm. Then R3 is again equal to R2, which is equals to 46.6 kilo ohm, right? Then take the relationship between C2 and R2, where R2 is equals to root 2 XC2. So you should be able to get the value of C2 after having modified the first equation in the design steps. So you would get C2 is equals to root 2. C2 is equals to root 2 divided by 2 pi FC into R2. Please check that equation. C2 is equals to, yes, it is correct, root 2 divided by 2 pi FC in R2, because XC and C2 are reciprocal to each other. So the root 2 goes to the numerator there, right? So you will get C2 is equals to approximately 400 nanofarad, because FC is given to be 12 kilohertz and R2 is estimated to be 46.6 kilo ohm, right? So then your C1 is equals to C2, very similar to how we had taken R1 is equals to R2 in case of the low pass filter, right? So C1 is equals to C2 is equals to approximately 400 nanofarad. Now comes the last part here, right? Estimate the highest signal frequency that will be passed. Now, one thing to be noted here is, when I speak about the high pass filter, right? So above the cutoff frequency, all the signals will be passed. That is what we know. But up to what value the signals will be passed? That is the next question. Correct or not? In the low pass frequency, that question doesn't arise. So from 0 DC to cutoff frequency, the cutoff frequency is finite. It may be 10 hertz, 100 hertz, 1 kilohertz, whatever it is. Up to that, the signal will be passed, beyond which the signals will be attenuation, and how long you will go, that becomes immaterial. But here, how long you will go in the pass band, that also is very important, and that is decided by the very specifications of your operational amplifier, which we call it as the unity gain cutoff frequency. I hope you should be able to recall what is the meaning of the unity gain cutoff frequency, right? It is the frequency at which the gain still remains unity, right? So now, as per the data sheets of IC715, right? So the unity gain cutoff frequency of IC715 is 11 megahertz, right? Anyway, that is not specified here in the problems. If at all they are asked in the examination, it must be specified, unless and otherwise you are provided with the data sheet of IC715. So now take the unity gain cutoff frequency FU as 11 megahertz. So obviously the highest frequency to be passed will be FU divided by AB, right? 1. So 11 megahertz. So from 12 kilohertz you should be able to pass all the signals up to 11 megahertz, which will restrict the physical limitations based on the operational amplifier characteristics. Beyond 11 megahertz, your operational amplifier itself will not be able to handle those frequency signals. So therefore, your pass band here will be remaining from 12 kilohertz to 11 megahertz. Though ideally it is 12 kilohertz onwards till infinity, right? So, but it will not be infinity. Practically, it is limited by unity gain cutoff frequency of the operational amplifier used, right? So, this is the simple example as far as the design of the high pass filter is concerned, right? Now, we shall move on to the next aspect, that is the band pass filter, wherein you will have the features of both the low pass filter as well as the high pass filter.